Here's a classic torque problem here that looks like an Atwood machine. It is an Atwood machine that you probably looked at early in the quarter. But the difference now is that we have a pulley with two masses hanging on it, but the big difference now is that the pulley is going to have some structure. The pulley is going to have a real radius and a real mass. So not like a pulley that's just sort of imaginary, that simply just reverses the direction of the torque. It's a real object that the two masses have to grapple with as it causes the rotation to happen. So what we'd like in the problem is the usual thing here. What is the acceleration of the blocks? Okay? So let's just get right at it then. Let's just see what sort of happens here if we get into this and see, well, what's the acceleration of the blocks going to be? We can start the problem using some things you already know here. In particular, just start identifying the forces on this thing here. There's a tension up like that, and there'll be an M1G down here, and a tension up like that. So we have a lot of the traditional things in there. Now, you ought to be careful about a couple things. Is we know the pulley is going to rotate, and we know that these tensions here now are going to sort of act on the pulley because it's going to rotate. We know there must be some forces on it which are going to cause torques, which are going to cause the pulley to rotate, and those forces on this pulley will be those tensions in there. Now there was a problem a bit earlier on in this video sequence here where we had a pulley like this, and it looked like that, and there were just two forces down like this and like this. I think this one was 20 newtons and this one was 30 newtons right here. So it's a problem like that, only it's more involved now. If a pulley is going to turn, there has to be some forces on it which can generate a torque, which can cause it to rotate. So it's sort of a problem like that, but the 20 and the 30 now, or whatever those forces are, come from these hanging masses right here. So a couple things you have that are different now from problems you may have worked early in the quarter like this. In particular, if this pulley is going to rotate, these two tensions cannot be the same. Because if this T was always the same as this T, the pulley wouldn't rotate because the net torque on it would be zero. So right off, you have to assume that these tensions in these ropes are not the same, exactly the same. So I'm going to call that a T1, and that's going to be a T1, and I'll call that a T2, and that's going to be a T2. So these sections of the ropes are the same sections. They'll have the same tensions in them, but as they cross over the pulley, the tensions don't have to be the same in the same rope on either sides of the pulley because that pulley is going to be rotating. Okay, so we got that label in there. The next thing that we have to be a little careful of is our sign conventions. As usual, we'll borrow a lot of stuff from things we did a few weeks ago. Namely, if this is negative, this is going to be positive, and that's going to be negative, that's going to be positive, that'll be negative, and that'll be positive right there. So tensions on opposite ends of a rope still have opposite signs. I'm just still following that. If down is negative, up is positive, down is negative, and when I go over, this better be a positive, a negative, and a positive. And we see the sign convention is nice and consistent. That negative motion corresponds to the system moving this way, and positive motion corresponds to the system moving that way. So what we'll do now is just the usual stuff. Let's sum the forces and on this block right here. So we know that A is the sum of forces divided by M. This is the usual thing here. I'll get a plus T1 minus an M2G over M2, and that's the acceleration on this first block here. I'll do the same thing over here. I know the accelerations are going to be the same because they're objects connected by a rope, so I'll get a minus T2 plus an M2G divided by M2. That's the acceleration of that block right there. So this is sort of the Newton's law analysis here, and we're doing quite well. We have a good section of the problem solved. We're not quite done yet because the unknowns here are T1, T2, and A. T1, T2, and A are the things that I don't know. That's three unknowns, but I only have two equations, so I need to find another equation somewhere. The way I'm going to find the other equation now is this is the new thing for the problem, is I need to analyze the pulley. What caused that pulley to rotate? So I'm not going to be summing forces on the pulley, but I am going to be interested then in finding the torques on the pulley, summing the torques on the pulley and dividing by the moments of inertia to see how all that's going to wash out. Okay? So I need to sum the torques on the pulley. So if I look very carefully at the pulley now, so I'd like to fill in this top right here with the sum of the torques on it. Both of these tensions are the forces that are going to drive the torques. And you can see they are acting at these 90-degree angles right here. And so let's write the torques down and see what we get, keeping in mind that our working equation for torque then is RF times the sine of theta. Moment arm times force times angle between the two. And in the case of this pulley here, this angle here is always 90 degrees, so the sine is always going to be 1. So really what I'm looking at is a moment arm times the force in there. That's sort of what I'm looking at. So if I look at this first tension over here, I can see that it's just going to be moment arm times T2. And the moment arm in this case here is always going to be the radius of the pulley because that's what they act at. So I'll see a R times T2. Now where that's coming from is when I look up here at this particular interaction right here, I see a torque being a moment arm times the T2. And remember, the sine of theta is 1 because there's a 90-degree angle in there. So there's moment arm times T2. And the same thing will happen over here. I'll have moment arm times T1. but in the negative direction, so I'll have a minus r times T1. Those are the two torques on it by the two tensions in there. And so now what I've generated is that third equation in here. So there, remember I had three unknowns and two equations. Here's my third equation, but it looks a bit suspicious. It looks like I've generated another unknown for myself, because what about alpha? Is alpha now an unknown? And I say no, it's not, because it turns out that the angular acceleration of the pulley is related to the linear acceleration of the block. In other words, these blocks just can't start zinging around without sort of being coordinated with that pulley in there. We know what that relationship is, though. Alpha is always equal to A over R, something like that. So I can come over here now and write an A over R in here is equal to R times T2 minus R times T1 over I, something like that. So I will end this sort of video right here with this substitution now, because now I have that third equation that we were looking for here. So when you look at the full analysis here, you have this equation right here, you have this equation right here. There's two equations that involve A, T1, and T2. Here's the third equation right here that involves A, T1, and T2. So you have three equations and three unknowns. And in a case like that, the algebra will take care of itself. So let me just, so you can go ahead and do that, but it seems like to me that you can now get some A equals to something. And what I'd recommend doing in terms of the algebra right there is I would solve this one up here for T1, and I would solve this one down here for T2. Get T1 equals to something and T2 is equal to something. Then I would do is I would plug your equation for T1 into this, your equation for T2 into this. Then you'll have just one big equation that involves only A's and R's and M's and I's, and solve for all this stuff so you can get A, but it will be a function of M1, M2, G, R, and I, but you can get that. Okay? So let's just rehash the problem real quick before we close the video and see what sort of new stuff's going on here. So we have this Atwood machine with a real pulley. There's some structure. There's a radius and a mass now. It's not just a pulley that flips the direction of the forces. Okay? So what we did then is one thing, new thing, is we had to sort of get at the point here that now, even though this is a continuous piece of rope, it doesn't always have the same tensions on both sides, because if it did, the pulley would never rotate. There has to be some different tensions in the rope. So we sort of hypothesized that, and there we go. There's the T1 and the T2 over here, where other problems, say early in the quarter, this would have been the same T. Not so here. But in the case like that, we just use Newton's law now. We sum the forces on this mass and get this equation, sum the forces on this mass and get that equation, and we got it here. Now, early in the quarter, these T's would have been the same, and you would have been able to solve and end the problem, but the T's are different now because the real pulley is sitting there, so we need to generate a third pulley now. So that's where this comes from right here. This analysis here was found by looking at the torque on the pulleys. That's a new thing for us right here. We've never done that before. Analyze the torques on the pulley as part of the force problem. We do that, and it looks like I accidentally erased part of it here, but we get an angular acceleration, which is related to linear acceleration, and the linear acceleration is the same linear acceleration as in those parts up there. So the algebra now will work out. You have three equations and three unknowns. You can solve for A and get your answer.